Hello and welcome to this video on Kirchoff's rule of radiation and black body radiation, or in less obtuse terms, why this strange device spins the way it does. As a general rule, when you see this device, known as a radiometer, or sometimes more or less often known as a röntgenometer, and try to get an explanation, you'll be told the black side of the card gets hotter than the white side and therefore pushes the card forward. Other times you'll be told that the photons hitting it are what causes it to push forward. Now, these answers are partly true and in many terms wrong, but the explanation only gives you some of the explanation, and ultimately little enough that it's a somewhat meaningless contribution outside of very specialized experimental designs. If you want to get a good idea about what photons can do, that's where you need a Nichols radiometer. Let's make this clear. There's a common misbelief, and one that originates with the very creator of the device itself, the Crookes radiometer, is that the momentum of the light hitting the dark side or the black face of the cards is what makes the radiometer spin. That isn't what's happening, and that's why we need to look into Kirchoff's law of thermal radiation. In very simplified terms, it says that a body at a temperature will radiate electromagnetic energy as a result of being at said temperature. Theoretically, this means that a perfect black body will have energy going in, and due to the thermodynamic equilibrium, absorbing that light and then reflecting it back out as energy. This is essentially the unique law of radiative emissive power. Now, this is universal for all perfect black bodies, and understand, there are bodies that are not necessarily perfect black bodies. And then again, there are those that are perfect. Take those terrible jokes as you will. There are more explicit definitions, but for this video, we have given you something that works well enough for now, but we also know there'll be some pedants, so to forgo those complaints, we'll at least try and summarize the more complex explanation with these short notes. First of all, you don't want a thin or light gas. It needs to be a dense gas, and this is because it will allow for the emission and absorption of radiation. That's important because you need both absorption and emission for this to work. Second, you need something that is able to get, to a certain extent, excited and therefore have energy jump between the orbits within it. That is to say, it must be able to go from the ground state to the excited state. This must occur in response to being hit by light and therefore form a photon, and that photon has to have an energy equal to the energy difference between what's going in and what's coming out, for all intents and purposes. Since we have different energy levels, they need to, at least to some extent, allow for this to occur, and therefore we need to have the initial baseline, or that is to say the ground state, and the excited state. Finally, we need it so that this only occurs at certain energies. That is to say, you need to hit it with a certain wavelength of light, for example, and that then causes the release of the photon. It shouldn't work at other wavelengths or frequencies. Let's be blunt about this. Kirchoff's law of thermal radiation is a refinement. It's not necessarily a thing in and of itself. It's a better explanation of what we're seeing, that being emissivity equal to absorptivity. In simplified terms, or at least a very abbreviated term. This is where our specific example is useful. Let's say you have a material, in this case, a panel on a rotating clock-like surface. One side of this is going to be illuminated by whatever your source of energy is. The other side is not going to be illuminated. Now, the side that's being hit by the light, because it's always spinning in one direction, will be colored black. Now, this is important as that black color allows for the absorption of that light energy at a specific frequency. This will then lead to the production of thermal radiation. That thermal radiation, for all intents and purposes, is the release of the excess energy above and beyond what that particular material can hold on to, and is the emission. This emission and absorption is absolutely key because it ensures that everything remains balanced. If you think of it as a scale or a seesaw, when you are adding something to one side, you need to add something to the other side, and vice versa. When you add something to one side, you add it to the other. Or if you take it away from the other side, you take it from the other, and again vice versa. Now, this is not a new idea. Let's be clear about it. The entire model goes back to roughly 1859, when Kirchoff's law of thermal radiation was formulated. But two things to note from this time. First of all the work at the time was entirely theoretical. There was no, let's say, experimental proof to show that this is what happens. And second of all, we do know that at least the initial explanation by the person who first postulated this wasn't correct. So that's a bit of a faux pas there. But we do know, using modern technology and experiments, that this is exactly what's happening. We know that, for example, it's not photons pushing it. We also know that it's not necessarily the energy itself, but how it's being emitted back out, and so on. One way we know this is an interesting experiment, let's call it, which involved the use of gold. Well, gold crystals to be precise. 2009 research at the University of Texas created basically exactly the same design. Something similar to the Crookes radiometer or light mill, just that each of the vanes, or those panels on it, was curved. This means you had a convex and a concave surface. Because the entirety of each of these vanes with its concave and convex surface was uniformly coated with gold nanocrystals, it provided a perfect absorptive surface, and it was a consistent absorptive surface on each side. Remembering though that absorption is only half of the equation, that being the left side of our balance here. Because each time the convex surface went past the source of energy in this case, it would get a little bit of photon energy applied to it, and it's a little bit more than the concave side did. Because of this, the gas molecules on the other side would get just a little more heated and give that little more energy to it. And this led to a difference in heat energy between the two sides, and that would cause the gas to move just a little bit. But because you had this occurring for each of the convex and concave surfaces, that difference in heating, the gas would basically push it just a little bit further forward. This would be a perfect demonstration of Newton's third law. Because you had practically nanoscale models of exactly what was happening, and were able to figure out what's going on in a three-dimensional space, in less complicated terminology, we had a real-world demonstration of this. You could see what was happening, and we could understand that no, it's not the photons pushing it to start with, and we know that it owes to the emission of that energy coming back out of it. And depending on the circumstances, this energy can either be in the form of visible light, or it could be in, say, radiation or something similar. There are all sorts of energies that can come back out of something once you have it absorbed into it in the first place. So it's basically you put something in, you get something out. This is used in our real world today for far more practical things than just ornamental desk things. Your doodads are nice and all, but they don't really make a world of difference. Although, then again, they don't make a world of difference in a lot of research. But it is used in things like, say, astronomy, to look at other planets, if possible, the stars, meteors, and so on. It gives us an idea of what, say, stars are composed of and what their temperature is. It allows for measuring Earth's temperature from outer space. It allows for monitoring for, say, climate change. It allows for better creation of, say, furnaces and ovens with reflective materials. Something, for example, if you want to maintain a high-level temperature, for example, a forge for making knives, swords, armor for the crusade, and so on. Or if you want to, say, make pottery and you need to ensure that the heat emitted from those pottery coils in your kiln works perfectly. These are the sorts of things you're looking at using. An engineer will take the knowledge about the various aspects of what the materials are and apply them efficiently to produce much better products. And of course, there are plenty of other applications in, say, science and engineering, but we're not going to go into the great depths there. Just understand there are plenty of applications in theory and in real world. But this is how you apply Kirchoff's rule radiation and black body radiation to a real world and use it, well, somewhat. If nothing else, it at least lets you correct someone. They tell you, oh yeah, I know how that thing works, it's this. And you can say, no, but... Anyway, thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. And please do post any comments, questions, or suggestions you have below